All right, hello everybody. Welcome back. Um, you should have the document opened up from Schoology or printed out. Anyway, it's called 3.1 Global Extrema. And the most important thing we'll talk about today is the extreme value theorem. Okay, but before we get an idea of how or what the extreme value theorem is, let's just look at these pictures here. So looking at this first graph right here, okay, if we're just looking at the picture that's given to us and we're trying to find the max is going to be at the highest point, which is right there, and that has a y value of 4. Okay, the minimum is going to be at the lowest point, which is going to be right over here, and so that's going to have a y value of 0. But now notice what happens when we go to the second picture. Okay, for the second picture, max is still the highest point, which is right here. So y value there is 4. However, there is no minimum. And the reason for that is because there's no point here. So if we were to get super, super close, right, you can say, well, we're close to 0, right? Maybe 0.00001, but even that's not the minimum because you could always argue, well, I can do better than that. I could do 0.0000001. And someone could say, well, I can do even better than that. And you can keep getting closer and closer to 0, but there's no actual value, there's no minimum. It doesn't actually hit 0. So basically, anytime we have an open circle, or an open interval, rather, so notice the difference here. Here we have a closed interval. Right? The beginning to the end is closed. Here we have an open interval. And so the extreme value theorem deals with the closed interval scenario only. Okay? When we have a closed interval, so if f of x is continuous on an interval, so let's go from a to b, and it has to be closed, not open, then f of x is guaranteed it has one maximum and one minimum. It was very easy when we looked at the first picture. We saw the highest point, we saw the lowest point, case closed, there was one max, one min. When we have an open interval, it's not as clear cut. There might be a minimum and a maximum, but as we saw here, in this scenario where we have a lower point, a lowest point is actually open, we can't say that that's a minimum. Okay, so we say none in that case. So the extreme value theorem guarantees us one max and one min if the function is continuous and closed on the ends. Okay? Now what we're going to be interested in is finding the extrema, finding the max or the min over an interval. Okay, and so here's the basic roadmap. Okay, so again, we're building on everything we've been working on. We're going to find the critical numbers. So to do that, okay, you're going to take the derivative, set the derivative equal to 0, and then those solutions or discontinuities, those x values will be the critical numbers. Okay. Number 2, maybe make a sign chart. We'll talk about that in a little bit. Okay, usually what we've done is after we find critical numbers, we do a sign chart to see what's going on. Is the function increasing or decreasing? So it won't technically be necessary, but it is a good idea, and I'll show you in a little bit. The third thing is we're going to evaluate the critical numbers and the endpoints, the x values. So we're going to plug in the critical numbers, we're going to plug in the ends, and we're going to see what the outputs are. Okay? And wherever the highest y value is, that's going to be the max, and wherever the lowest y value is, that'll be the min. Okay, and you can kind of see why we could technically skip step number 2, because if we're just going to plug in all the critical numbers and endpoints anyway, then technically we don't need to see if the function is increasing or decreasing. We just want to know what the value is at that point. However, making a sign chart, you will see that you can sometimes skip testing some of those critical numbers. Okay, so let's put all these steps to use, looking at the first example here. So first, we're going to find the critical numbers. So that means we got to take the derivative. So the derivative here will be 1 plus cosine of x. Now we set that equal to 0. We solve. So cosine of x is equal to -1. And here we get x equals pi. And that's certainly between 0 and 2 pi. So that's good. And so now we're going to do our sign chart. Again, maybe you want to skip this, but I'll show you why it's not a bad thing to do. So here's f prime. And actually, let me change, since we are closed, let me change my number line to closed instead of infinite. And I'll put the endpoints, 0 and 2 pi on the ends. And now all the critical numbers, in this case just one of them, and I'll just go in between. All right, and remember we're going to test, right, we're going to figure out what's going on with the derivative. Is it positive, is it negative? So I'm going to take maybe pi over 2, plug pi over 2 into 1 plus cosine x, right? That's what we're going to do. Cosine of pi over 2 is 0. Add 1, that's positive. And now a number that I can test here might be 3 pi over 2. 3 pi over 2 plugged into the cosine of x. That's going to be 0 as well. Add 1, positive. Okay, and so here's the value of making a sign chart. Notice that the graph is increasing from 0 to 2 pi. So there's no need to test pi. Okay? Whatever you test there, it's going to be higher at 2 pi because it's increasing. Does that make sense? So anytime you have this pattern where you have positive and then positive, or negative then negative, surrounding a critical number like pi, you can skip testing it. Okay? So now we're on to step 3. We're going to evaluate. So what is the function equal to at 0 and at 2 pi? And again, you could test pi, but it's not necessary. So in this case, all we're doing is testing the endpoints. So I'm going to use EP to show that. We're testing the endpoints. If I plug 0 back into x, right? So we're doing 0 plus sine of 0. Well, that's going to be 0. If I plug in 2 pi, 2 pi plus the sine of 2 pi, that's also going to be 0. Or I'm sorry, that'll be 2 pi. 2 pi plus 0, which is 2 pi. And so we are done. Okay, the highest y value is 2 pi, so the max is 2 pi and that's when x equals 2 pi, and the minimum, and I should say these are absolute max and absolute min, right? The absolute max is 2 pi when x is 2 pi, and the absolute minimum is 0 when x is also 0. Okay? So again, just to clarify, these over here, these are the y values, right? So this is what we're checking to determine which of those points or which of those values is going to be the min or the max. And it's a coincidence, but here, the numbers that we're plugging in, right, these are the x values. Okay, in this case, they happen to match, but that's not always going to be the case. All right, so that's essentially how it works. Now we'll just go through a few other examples. Let's go green here. Okay. So again, find the extrema, and we could probably talk about this a little bit here. The fact that they don't use the word relative, right? That's why we're not doing the positive and negative chart and paying attention to all that, because we're not talking about increasing and decreasing and just looking for relative minimums and maximums. We're just looking for the total minimum or global or absolute minimum and the global or absolute max. 1 point, okay? One value for each of them. So again, following the procedure we outlined, take the derivative so that we can find the critical numbers. The derivative will be 12x cubed minus 12x squared. And we can certainly factor that a bit. Take out a 12x squared, you get x minus 1. Set that equal to 0. Looks like the critical numbers are going to be 0 and 1. And now we do a sign chart. Again, optional but helpful. Negative 1, 2, those are the end points. And now 0 and 1 happen to fit between negative 1 and 2, so we'll put both of them in there. And let's see what's going on. So I'm going to test negative 1/2, positive 1/2, and I'll do 1.5. So those are the numbers I'm going to plug in to the derivative to see whether it's increasing or decreasing. Okay? If I plug in negative 1/2, when you square it, it's positive, but then over in the second factor, negative 1/2 minus 1 is negative. So that'll be negative. Plug in positive 1/2, it's going to be the same exact story. It'll be positive times negative. If you plug in 1.5 now they will both be positive, and so we get positive overall. Okay? And so right here, since we have decreasing to start, continues decreasing until we get to 1, we can skip 0. Okay? So now when we test all our points, okay, we're going to test the endpoints. So again, this is an endpoint. And then we have a critical number, which was 1. So we plug 1 in. And we also have another endpoint at 2. Okay, so we plug both of those in. If you plug negative 1 into the original function, you're going to get 7. If you plug 1 into f, you're going to get negative 1. And if you plug 2 in there, you're going to get 16. Okay? And so, conclusion, negative 1 is the minimum when x equals 1. And 16 is the max. Sorry about the noise. There's construction going on next door, and of course they had to pick right back up as soon as I started recording the video. And this is when x equals 2. Okay? All right, hopefully this is making sense. It's the same roadmap no matter what the function looks like. You just got to remember how to take derivatives, basically. Otherwise, you have no chance, right? Because if you can't do the derivative right, then you're not going to get anything else after that correct. All right, so third example. Let's go blue. All right, so we have a quotient. And so I will do the quotient rule to to find my derivative. So low d high minus high d low over low squared. Let's simplify that a bit. So we get x squared plus 1 minus 2x squared all over x plus 1 squared. You can clean that up a bit, 1 minus x squared after you combine like terms. That's about as good as it gets. Oh, I guess we could factor. 1 minus x, 1 plus x for the numerator using difference of squares. And so now we set that equal to 0. And from there we get our critical numbers. We're going to get 1, negative 1. And if I take x squared plus 1 and set it equal to 0, I mean, that's never going to happen, right? Because x squared does not equal negative 1. So we do not have any critical numbers from the discontinuity aspect. In this case, we just have the two critical numbers from the zeros of the function, which are at x equals 1 and negative 1. All right, so now on to the sign chart. Endpoints, negative 3 and 2. The critical numbers in between are negative 1 and 1. And again, pick some numbers, plug them in, and see what's going on. So I'm going to plug in negative 2, 0, and maybe 1.5. If I plug in negative 2, and I'm going to go to the simplest version of the derivative being right here. Okay. If I plug in negative 2, we get positive, negative, positive always in the denominator. So that's going to be negative. If you plug in 0, you get positive, positive, positive. So that's positive. If you plug in 1.5, you get negative and then positive over positive. So that'll be negative. All right, so in this case, we have to test everything, the endpoints and the critical numbers, because we switch from negative to positive, positive to negative. So we do got to check all of them. So first endpoint, we have f of negative 3. Then the critical numbers come next. I'm just going in order from smallest to greatest. So we're going to plug in negative 1. We're also going to plug in positive 1. And now the last point we check is the end point on the right, which is 2. All right, so again, now we are, oh, and I guess these are G's. Oh, my bad. Not F's. And this is sign chart for derivative of G. Okay. So if I plug, so now we're going back to this. Oh, wrong one. Back to this, right? When I plug in, when I evaluate, we always go back to the original function. So plug in negative 3, you're going to get negative 3/10. Plug in negative 1, you're going to get negative 1/2. Plug in 1, you get positive 1/2. Plug in 2, you get 2/5. All right, and so here's the min. The smallest value, the most negative, I guess, would be negative 1/2, and the highest value would be the positive 1/2. So in this case, we have an absolute min of negative 1/2 at the x value of negative 1, and absolute max of positive 1/2 at x equals 1. Okay. And now for the last example, same thing, take the derivative. Now we have a product. So imagine we got two different functions here, f and g. So we got f times the derivative of g, which is still e to the x, plus f prime, which is 2x, times g, which is e to the x. set that equal to 0. And we could probably factor, take out an e to the x, since that's and also an x. So take out e to the x and x. That's going to leave you with just x plus 2. Okay, and let's go ahead and find the critical numbers. So from the first factor, you got x equals 0. From the second factor, you get x equals -2. And so now we go to our sign chart. So we're going all the way from -3 to +1, keeping in mind that we need -2 and 0 in there. And, you know, I want to test -2.5, maybe -1, maybe +0.5. Okay, and we're going to go into the simplest version of the derivative. So that would be this one. So I'm plugging these test values into the simplest version of the derivative. E to the negative, remember, e to the -2.5. That's not negative, that's just 1 over e to the +2.5. So keep that in mind, right? So when you plug that in, that'll stay positive, but it's this x right here, right? That's what we're going to pay attention to. That makes it negative. So we got a negative on the outside, a negative on the inside, so this will be positive. If I plug in -1, we have a negative on the outside and a positive on the inside. If I plug in a half, we have positives all around. Okay, so we got positive to start, so that means the f prime is positive, and then negative, and then positive. And so we do have to test all our values, endpoints and critical numbers. So endpoint, then we have 2 critical numbers. And so we're going to plug in -3, -2, 0, and 1. If you plug in -3, again, now we're going back. Let me highlight this different color. Nope, that's too... So these values are getting plugged into the original function, right, to figure out what we're going to get. So when we do that, -3 squared is 9, so we get 9e to the -3. Here we'll get 4e to the -2. Plug in 0, you're just going to get 1. Oh no, 0, sorry. 0 times 1 is 0. Plug in 1, you're just going to get e. Okay. So now this number, that's the same as 9 over e cubed. This is the same as 4 over e squared. Both of these denominators, e cubed is bigger than 9. E squared is bigger than 4. So these are a little bit bigger than 0. So 0 is the min, and e is the max. And so the final conclusion here is that the absolute max is e, and that's at x equals 1, and the absolute min is 0, and that's at x equals 0. All right, and that's it for the notes for this section. So hopefully this makes some sense. We've been kind of building up to this. If there's any questions, please jot them down, and we can certainly go over these next time we meet. All right, until next time.